1 half, plus 1 quarter, plus 1/8, plus 1/16, and so on, forever. What happens when you add infinitely many numbers together? Does the total explode, growing bigger and bigger without limit? Or does something stranger happen? Does it actually settle down, landing exactly on a specific number, even though you never stop adding? Some infinite sums spiral off toward infinity. Others land precisely on a single value. This is what it looks like when one converges. Let's watch it happen, one term at a time. After the first term, 1 half, your running total is 0.5. Add the next term, 1 quarter, and the total climbs to 0.75. Add 1/8, and you're at 0.875. 1/16 more, and you're at 0.9375. 1/32 more, and you're at 0.96875. Watch the pattern. Each new term is smaller than the last, and each partial sum edges a little closer to 1, but notice something important. None of these partial sums ever reaches 1. None of them ever passes it, either. They just keep marching forward, closing half of the remaining gap every single time. That's the heart of convergence. The partial sums approach a specific number, getting arbitrarily close to it, without ever overshooting. Here's the same idea, but visualized as area instead of distance, and it makes the convergence almost impossible to doubt. Start with a square, and say its total area represents the number 1. Shade exactly half of it. That's your first term, 1 half. Now take what's left, the unshaded half, and shade half of that. That's 1 quarter of the original square. Take what's still left, and shade half of it again, 1/8. Keep going. 1/16, 1/32, 1/64. Each new shaded region is half the size of the last leftover space. Watch what happens as this continues. The shaded region creeps closer and closer to filling the entire square, and the tiny unshaded corner that's left keeps shrinking, cut in half every single step. No matter how many times you repeat this, there's technically always a sliver left over, but that sliver shrinks toward nothing. In the limit, after infinitely many steps, the shaded area fills the entire square. Exactly 1. Not approximately, exactly. Formal definition. This is actually the formal mathematical definition of convergence, stripped of any mystery. A series converges when its sequence of partial sums approaches a single, specific number. We give that running total a name, call it S sub n, the sum of the first n terms. For our series, S sub n is the sum, from k equals 1 to n, of 1 over 2 to the k. Convergence just means, as n goes to infinity, S sub n approaches a fixed limit. In this case, that limit is exactly 1. That's it. No hand waving. No, getting infinitely close, as some vague poetic idea, just partial sums that provably settle on one number as you add more and more terms. But here's the catch. This doesn't happen automatically just because you're adding infinitely many things. Take the simplest possible counterexample. 1 plus 1 plus 1 plus 1, forever. Every partial sum is just the term count itself. 1, 2, 3, 4, and so on, climbing without any limit. This series diverges. It doesn't approach any number at all, it just grows forever. Here's a sneakier example. 1 plus 1 half plus 1/3 plus 1 quarter, and so on, the harmonic series. Each individual term does shrink toward 0, just like our converging example did. You might expect that to be enough for convergence. It isn't. Despite the terms getting smaller and smaller, this series still diverges. Its partial sums grow without bound, just extremely slowly. So shrinking terms are necessary for a series to have any hope of converging, but they're not sufficient on their own. Something more specific about how fast the terms shrink determines whether the sum settles down or drifts off toward infinity. So that's what convergence really means. Infinitely many steps, but one finite destination. You can keep adding forever. 1 half, 1 quarter, 1/8, on and on without end, and yet you never leave the square. The total edges closer and closer to exactly 1, and never breaks past it. Infinite process. Finite answer. That's the whole idea.